All right, and we're back. So, this chapter is all about exponential equations, right? Exponential functions. Ones that increase at an exponential rate. Meaning, algebraically meaning that if I take a number raised to the x power, that's an exponential function. So, we talked all about what happens if we change the number. You know, what happens if it's less than 1, it would be a decay. What happens if it's greater than 1, it's going to be a growth. If it's at 1, it's a horizontal line. But what happens if we choose a base, a very particular base called e? Of all the possible bases for an exponential function, there is one that is most convenient for purposes of calculus. And it's most convenient when we talk about naturally occurring things. Okay? The choice of a base is influenced by the way the graph of y is equal b to the x crosses the y-axis. One key piece here is the y-intercept, where it crosses the y-axis. Because notice that wherever it crosses the y-axis, that's the base, right? Or that's the number being multiplied to the base. It always crosses the y-axis at 0, 1. You know, if I take anything raised to the 0 power, it's always 1. So 2 to the 0, 1. 3 to the 0, 1. 4 to the 0, 1. 5 to the 0, 1. E to the 0, also 1. So no matter what I choose to make my base, it's always going to happen at the location 0, 1. But what is happening at that location is extremely important. Figures 13 and 14 show the tangent lines to the graphs of 2 to the x and 3 to the x. Now, when I talk about a tangent line, we're going to discuss tangent lines at great length. But when I talk about tangent lines, just for our purposes right now, you know, back in geometry, we talked about tangents being something that's going to lie directly next to a circle. That's a tangent line to a circle, right? Where it's only going to hit the circle once. It's only going to lie close to that circle one time. Okay, and you can have an infinite amount of tangents on a circle. Right? No matter at all points around the circle, there's exactly one tangent line. And it's always, you know, in geometry we learned that it's always actually perpendicular to that radius. But that's not really calculus, that's more geometry. Now, so for our purposes, all we need to know is that the tangent line is going to lie directly next to a curve. Directly next to a curve. Take a look at these two diagrams. This one is 2 to the x, this one is 3 to the x. And what we're going to examine here is the slope of the tangent line. Excuse me. The slope of the tangent line. Notice that the slope, and this is just an estimate of the slope, and we'll talk about how we figure out this. Actually, like 2/3 of calculus is all how do we figure out the slope of the tangent line at any given point. The slope of the tangent line here at 0, 1 for 2 to the x is 0.7, about roughly 0.7. The slope of the tangent line here at 3 to the x is 1.1. So notice here that the slope is below 1 for 2 to the x and above 1 at 3 to the x. And we can kind of guesstimate that if I truly wanted the slope to be at 1, at 0, 1, then my base would need to be something a little bit closer to 3 than it is to 2. Okay? For purposes, we can think of the tangent line. If we measure the slopes of these tangent lines at 0, 1, we find that the slope at 2 to the x is 0.7. The slope at 3 to the x is 1.1. Scrolling down here. It turns out, as we will see in chapter 3, that some of the formulas of calculus will be greatly simplified if we choose the base b so that the slope of the tangent line, if y is equal b to the x, is exactly 1. Has to be exactly 1. In fact, there is such a number that it's denoted by the letter E. This notation was chosen by the Swiss mathematician Leonard Euler. Yeah, that's how you say his name, Euler. E-U-L-E-R is Euler. Leonard Euler in 1727, probably because it's the first letter of the word exponential. We're not really sure. I always have people say, oh, that's the first letter of his last name. That's why it's E. No, that's not really the case. It's more for something standing for exponential. 2 years ago, I took a history of math course. One of the classes that I had to take was a history of math course. It was like the coolest thing in the world. I did my whole final project on Leonard Euler. Oh man, he was a great guy. But he was around like a little bit before Revolutionary time, right? 1727. That's when he did his big stuff. And he did a ton of stuff in math. I mean, he did stuff in graph theory and number theory, as well as a lot of calculus stuff. In view of figures 13 and 14, it comes as no surprise that the number e lies between 2 and 3. Right? We talked about it. It's probably closer to 3 than it is to 2. It actually turns out that it's 2.71828 and so on. It's going to vary a lot. Y is equal to e to the x lies between the graphs of 2 to the x and 3 to the x. In chapter 3, we will see that the value of e, correct to five decimal places, we'll talk a lot more about e later on. But for our purposes right now, we just need to know that e is a little bit closer to 3 than it is to 2. It's 2.71828. It's an irrational number that's going to kind of go random, right? Just like pi 3.14159, it does not have any terminating or repeating decimal places. Same thing with e. We call the function f of x is equal to e to the x the natural exponential function. It's called the natural exponential function because things in nature, tend to go to this number, this 2.71828. This thing naturally occurs very often. Euler kept finding more things and more things and more things that were kind of limiting to this number, like going to this number. So he defined it to be, instead of writing it out each time, he defined it to be e. But again, what another unique thing, and especially for calculus, unique thing is that if we take the slope at 0, 1 of e to the x, and this is the graph of e to the x in the middle there, if we take the slope of that tangent line, it is 1. Okay, the slope of that tangent line at 0, 1 at its y-intercept is 1. So first thing we're going to do here is graph the function y is equal to 1/2 e to the negative x minus 1, and then we're going to state the domain and range. Okay, so I see 3 transformations going on. I'm going to do it using the transformations, and then I'm going to plug it in my calculator to kind of confirm what we think is happening. I see 3 transformations going on. And again, think about order of operations. If I plug in a value for x, what happens first? Which transformation happens first? What's going to act on it first? If I plug in the number 2 in for x, what's going to act on it first? The negative, right? The negative is going to act on it first. So that's my first thing. What is that negative up in the exponent mean? Reflection over what? Reflection over the y-axis. Reflection over y. And it's a reflection over the y-axis because I'm changing the x value, right? And if I'm changing the x value, it's something horizontal. That means the reflection across the y-axis. All right, so say I plugged in 2, I would take e to the negative second and then multiply it by 1/2. Multiply it by 1/2. What's that multiplying by 1/2 going to do to it? Vertical. Good. Vertical compression by 1/2. And then the minus 1, down 1. Okay, so let's sketch this, and then let's go to our calculator to see if it's actually true. Now I'm going to get real fancy here. Here is y is equal to e to the x. So here's 1, 2, 3. We know that the slope at 1 is 1, so it's generally looking like that. Reflection over the y-axis. Okay, you guys are going to be baffled by this. Flip, horizontal, left, right. Ooh, I'm so close. Still got to cross there. That's a reflection over the y-axis. Vertical compression by 1/2. Okay, I got it. I can't really do any transformation like that. Vertical compression by 1/2. So vertically compressed. Okay. Vertically compressed. It's going to distort it by pushing it down toward the x-axis, right? So can I do that? Let's see. Can I No, I can't. I can't change the aspect ratio. No, I can't. So I'm just going to have to take this and now let's draw another one on top of it. So shrink it down toward, actually, you know what? I should go 1/2, right? So it's going to go here. It's going to make it even more shallower though. Again, this is a sketch. Ooh, yikes. That's a bad sketch. And then go down 1 unit. So I'm going to take this red line and go, no. Ooh, lost. Sorry, buddy. Lost your arm there. Okay, let's put it in our graphing calculators to see if that actually was the case. Because again, the goal of all of these transformations is, can we visualize what's going to happen without actually needing to graph it? So 0.5, remember E is right below pi, the division symbol. E to the, I'm going to put, oops, that's pi, to the, put this in parentheses, negative x, negative x, there we go, and then minus 1. I'm going to zoom 6, and hopefully it looks something like our red. There it is. Mine's a little bit more shallow. My sketch was a little bit more shallow. But we get generally in the right direction here. All right, but now let's talk about its domain and range. Let's talk about its domain and range. What about the domain? Is there any restriction on anything that I plug in for x? Is it going to go forever left and right? Yeah, so domain is all real numbers. So domain is negative infinity to positive infinity. But now, remember that the range is going to level off, isn't it? The range is going to level off. It's going to level off to what, though? Think about the parent exponential. Isn't it leveling off to the x-axis? Like, isn't the asymptote the x-axis? So therefore, it was going at 0. Does the reflection across the y-axis change the asymptote? No. Does the compression change the asymptote? No. Because it was the axis, right? Because it was the x-axis. And then we moved it down 1 unit. So the range is from -1 to infinity. And it will not reach -1. Okay. All right. Let's take a look at this last problem that we have. Use a graphing device to find the values of x for which e to the x is greater than 1,000,000. All right. I want you to estimate it. Before we actually put it into our calculator, I want you to think about how big does x have to be to make e to the x 1,000,000. I want you to write down a number. E to the 10th? I don't know. E to the 15th? E to the 18th? I don't know. What do you think? I want you to physically write down a number. Guess at, okay, 2.71828 raised to the what power is going to be 1,000,000. Million. I want you to actually think about it. Okay? Yeah, guess. To me, it's like, okay, to get up to 1,000,000, it's got to be a big number, right? And maybe in the, I don't know. Maybe in the 30s? I don't know. See, I know better because I've done this example already. So let's go to our calculators here. Let's go to Desmos. And I'm going to see here. Yes, graphing calculator, thank you. In one side, I'm going to do e to the x. And in the other one, I'm going to do 1,000,000. And I got to do y equals 1,000,000. Okay. Now, I can actually go in and change my window in the settings. And so I'm going to make my y-axis 1,000,000. Let's go like 1,100,000. Oh no, let's not go that far. So 100. Okay, there it is. Okay. I see my y equals 1,000,000. Let's see. Where's my intersection point? 13.8 is the number. 13.8. Who got the closest? Anybody say close to that? What'd you say? 15, that's pretty close. See, I was guessing like up in the 30s somewhere. That means that I only need to take e to the almost 14th power. e to the 14th would get you over 1,000,000. Isn't that crazy? Like just to the 14th power, get you all the way up over 1,000,000. What I'm trying to stress to you guys here is that that's how fast exponential equations grow. Okay, that's how fast exponential equations grow. I only needed to get out to the 14th x value to get way up over 1,000,000. Okay, exponential functions grow very fast, way faster than any polynomial equation, way faster than any like quadratic equation. They go pretty fast. All right, so that's all I have for today. I'm going to shut off the video and let you guys work on your